Welcome everyone. Let's slowly start. It is my great pleasure to introduce Jeongwan Haah, today's APCTP colloquium speaker. So although I do not feel to introduce about him, so let me briefly introduce. So his career, and he graduated Seoul National University in 2008, Korea. So in physics and mathematics. And then he moved to US and go to Caltech, and he got PhD. In 2013, his advisor was Professor John Preskill. So his thesis title, Lattice Quantum Cause and Exotic Topological Phases of Matter. Then he moved to MIT and he got a MIT Topological postdoctoral fellow from 2013 to 2016. And he moved to Microsoft Quantum and senior researcher until 2019. Now he is a principal researcher in Microsoft Quantum, Washington. So I think he's quite famous. Particularly, he is the original author in this Fracton business. Particularly, his paper in 2011 entitled "Local Stabilizer Codes in 3 Dimensions with a String Logical Operator." So nowadays, this code is named as Haah's cubic code model. And interestingly, he selected his 5 articles, and one of them is I already introduced. The other is 2013, Quantum Self-Correction in the 3D cubic code model. And 2018, this is also very well known, operator spreading in random unitary circuits. And interestingly, nowadays, the famous X cube stuff is not selected by himself. But anyway, yeah, this will be introduced, I guess. So I think, yeah, we are ready to run. So it's your time, please. Yeah.
Thank you. I'm very happy to be here. Yes, today's talk is concentrated around the quantum error correction in relation to the many-body physics, especially anything that smells like a topological. Okay, let's begin with a little bit of history. So in the 90s, something amazing happened in the intersection between computer science and physics. 92, Deutsch and Sosa come up with an algorithm that had a quantum speed up. They considered a question whether a given function is a constant or balanced. Well, so they considered a promised problem where a function is promised to be either a constant function, so every input you get always the fixed outcome, or it is balanced. As exactly half of the input is valued at 0 and the other half is valued at 1. And the computational task is to distinguish them, the 2 cases. And here the figure of merit is to minimize the number of function evaluation. Classically, if you do not allow any error, your answer must be always correct, then the minimum number of function calls has to be at least more than the half of a possible input. Similarly, there is a related problem called the Bernstein-Vazirani problem, and here is a little bit different problem. You're promised to be given a linear functional, so there is some vector space, and there's some unknown linear functionals which outputs a value, and you have to determine what that linear functional is. Classically, you would have to evaluate each coordinate to read off that linear functional coefficient, but quantumly, in both cases, you only need one evaluation of the function. And this led to the Bernstein-Vazirani algorithm, now it's called, is used to bootstrap. It was bootstrapped to Oracle separate so-called computational complexity classes BQP versus BPP. It's an acronym of bounded error quantum polynomial time algorithm and bounded error probabilistic polynomial time algorithm. So BPP stands for something that you can solve on a classical computer if you have access to randomness, and BQP is a similar thing, but you're now given to access to quantum machine. People are still wondering the exact relationship between these two classes and how large is the BQP beyond BPP. No one believes that those two classes are equal. If they were equal, then that means that quantum computer has no advantage over classical computers up to polynomial reductions. So this discovery led to immense interest in the quantum algorithms. And a couple of years later, Peter Shor, who is now at MIT, who was then at AT&T Bell Laboratory, found a factoring algorithm. Recently, Shor posted some historical remark on this finding, and there was an interesting piece. Initially, Peter Shor did not find the factoring algorithm, but found algorithm to find discrete logarithm. And then that news spread became a rumor because he gave a talk at some point. And Umesh Vazirani called Peter Shor, "Oh, I heard that you found the factory algorithm," which was not true at the time of Shor gave the talk, but in between the rumor and the call, Peter Shor fortunately found the factory algorithm and finished the proof. And later he published the paper, and now that's known as a Shor's factoring algorithm. There was a criticism that quantum mechanics is described by continuous variables, the state vector. Even if your degrees of freedom are qubits, the discrete entities, the quantum states live on a continuous space. So how is it different from an analog classical computer, which is not scalable? There's no error correcting possible for analog machines. So isn't quantum similar? That was the criticism. And Shor answered this criticism by showing that, oh, quantum is different because we can essentially discretize the errors and we can error correct. And here's how we can correct at least one error. And here's a concrete way to do that. And that's the reason he introduced this 9-qubit code. Shortly after, yes.
Sorry, before we further, I don't understand the meaning of the question itself in the first line. Why is it important? Is a function constant or balanced? So what does it mean?
Sorry,
yeah.
So it's a typical setting in the computer science. So, well, in computer science, what does a problem mean? Problem means that there should be a class of questions, and there should be a class of inputs that are allowed by the questions, and there should be an answer. So all these three pieces must be very precisely defined. Otherwise, it's not a well-defined problem. So Deutsch and Sosa considered a class of questions, and the question is to determine between two cases. One case, you're given a function in a black box. So you're literally given a black box. Imagine that. And there's an input button. So you write down some scribble. You can enter a number at your wish, plug it into a machine and press a button, and the box will tell you the output. And this relationship is supposed to be a function, and this function is promised. In other words, your black box is behaving in one of two ways. In one way, the function is constant function. Your black box outputs, regardless of the input, the fixed value. Or the second case is that your box is outputting either 0 or 1, but exactly half of the input, the box gives you 0. Exactly the other half, the box gives you 1. And your task is to distinguish two cases. And that's the question. I was just specifying what the question is. Well, the precise class is not that important.
Is it an important question? In what sense? Sorry.
Importance is a sociological thing, so let me not comment on that. But it is interesting, certainly interesting class of function, because if you're going to answer this question without any error classically, then you have to press the button of your box for more than half of the possible inputs. Otherwise, you cannot determine the answer without any error. Now, quantumly, interestingly, you only have to press the button once, regardless of the input size. That's the interesting piece. So there is some quantum, quantum the assumption that the box behaves quantum coherently gives you a computational advantage. And the task is, well, now the academic question is, how is this advantage? How much is this advantage? Quantify it. That's the academic question.
I see. Thank you.
And practically, of course, useless. It's not that. Okay, let's move on. And quickly after the discovery of the 9-qubit code, the first quantum error correcting code, group of people come up with the family of error correcting code. And shortly after, Manick-Neal and Ray Laflamme come up with a quantum error correcting criterion. Here, pi is the projector in your Hilbert space, whose range, the codomain range is your code space where your encoded state should live in. And the criterion says that if you sandwich that code space projector with some observable, then that observable should, then the product of that, the observable sandwiched by the projector must be a scalar multiple of the projector. We'll come to this criterion a little bit later. And then remarkably, there is important threshold theorems that are that was being proven for increasingly large scope of error models. So what's this threshold theorem? So here's a statement. There exists some constant number, people call it threshold value, such that whatever quantum circuit you give me, it's a circuit that does some particular task, consists of, say, n gates. In the classical world, that n would correspond to number of, it corresponds basically the number of lines you would write in your source code. Then, given such any quantum circuit, there's a transformation to an equivalent circuit doing the same task in the absence of any errors. And that transformed a circuit consists of slightly larger number of gates. How large? Some polylogarithmically large gates. And this transformed circuit behaves almost identical. It's 99% of the time when you run it, because there is some randomness because when you measure things, it almost always gives you correct answer if the error rate per physical gate is below that value. Here it is important that this value is fixed and it works for any quantum circuit. And transformation rule is given for all quantum circuits of this sort. So this is this value being universal that's the important piece. And in this polylogarithmic factor, by the way, there's a terminology maybe barrier or difference. When you hear polynomial, in math literature, polynomial is usually used as a noun. So it refers to literally polynomial. But when it's used as an adjective, like polynomial complexity or polynomial number of gates or something, it means power law. Okay, so in this polylog n is the number of gates. what do we need? You need a definition of logical qubits that is protected against physical errors, and you need an appropriate error correcting protocol to how you have to specify how those logical qubits must be protected. And usually such a fault-tolerant protocol is realized by some error correcting code, which is basically the identity gate at the logical level that keeps your quantum coherence in a corner of your Hilbert space intact from other physical noise. And such a fault-tolerant scheme and the noise physics, the detail of noise physics and parameterization of the noise strength and so on, those details determine specific values of this threshold. So mathematically, the only important piece is that the threshold is positive, non-zero, but practically the higher, the better. Of course, when you say threshold is high, you have to ask what the noise physics is, how your parameterization of the noise strength is, and so on. So those details matters a lot. And given such a theorem, people have now we want to construct the real quantum computer, and a typical stack or hierarchy for fault tolerance is as follows. You first need a qubit, of course, the physical qubit. Prevalent choice for qubit in these days, well, there are many platforms. Here I'm showing a harmonic oscillator with the slight n-harmonicity realized by some Josephson junction usually on a superconductor. And this platform is adapted by many companies, including Google, IBM, and others. Microsoft is pursuing after the Majorana-based qubit, which is basically proposed in the Kitaeus 2000 paper. You have a wire whose end modes with the when the wire is placed approximate to a superconductor, it develops a zero modes at the end of the wire, and that can be used to protect the qubit. And given such a qubit, it can be anything. Well, it can be something else. For example, the Yale group is experimenting with the photons on a optical cavity. Intel has some experiment with using spin degrees of freedom, and experimentalists at Harvard are using atoms and their internal structure as a degrees of freedom to use as a qubits and so on. Once you're given that qubits, then people consider specific error correcting codes. There, the technology of Pauli matrices and syndrome measurements and all the theoretical knowledge about error correcting codes is used. Why Pauli matrices are used? It's primarily because it's easy to understand, and mathematics is relatively simple. All measurements are given by projective measurements. There's no complicated P of M involved. And once you measure out your physical qubits and try to encode the logical qubit, then the correction procedure is also at least conceptually simple. Often you don't have to do anything. You just have to relabel what you mean by Pauli X or Pauli Y or Pauli Z. That's all that is needed. On top of that, once you have that error correcting code, then there's a logical operation. And this logical operation depends on what error correcting code you choose. And depending on this code operation, the set of logical operation primitives also changes too. So some holistic view is necessary to design a truly functional logical qubit, but roughly these three stages are taken usually. Now,
a question.
Yes.
So, sorry, in one page before, please. Yeah, here let me try to understand. If I consider classical computer, so is this threshold theorem also applicable to such classical computer, or it is?
Yes. there is a classical threshold theorem. I think it probably dates back to von Neumann area. The form of that threshold theorem is exactly the same. Actually, yeah, it's exactly the same. The threshold value is probably very high in the classical regime because the error correction is much simpler in the classical. Even these items like logical, just erase Q, logical bits and gates, then yes, everything applies in the classical regime too. These days, this threshold theorem is almost completely irrelevant because the classical hardware is so reliable. Most of your computer, the CPU and RAM, they don't make use of any error correcting code, but still very fiducial. If you go to interstellar communications, like a deep space science project, if you send the machine to Mars, or in that setting, you do need fault tolerance. And even like the electric cars these days, the reliability of the machine helped driving capability is so important. So some manufacturer implements 3 identical computers and let them do exactly the same calculation and compare the result. And if they agree, then they do to implement it in real life.
I see. Okay.
Can I ask a question as well in the same page about this threshold theorem?
Yep.
Yeah, you said this P threshold, the threshold probability or the threshold error rate.
Yeah.
It is universal or independent of. I guess what you meant was that this PTH is independent of this large N, so kind of this quantum circuit size. Is that what you meant?
Yes, that's the most important piece. But the very value of the threshold is a function of noise physics and your choice of fault-tolerant scheme. You can optimize that threshold value over many fault-tolerant schemes and seek for some universal value. But that attempt is now discouraged by this piece. Your noise strength is not a. There are many metrics to measure your noise, and that washes off your universality.
Okay, thank you.
So since we are talking physics, we cannot ignore the influence from physics into the error correcting code. So far, everything is kind of computer science, and physics only provided the device. But even at the fault tolerance level, physics has played an important role, and it dates back to early 70s or even older. There is a discrete gauge theory. When you hear gauge theory, if you're coming from a physics background, then you would probably, as I did too, imagine the Maxwell theory. You have a field strength with a gauge field A, and you can consider the gauge transformation. A goes to A is transformed by a derivative, and you can start the Lagrangian, and you write the field theory, and you analyze them. You can do almost the exact content on an extremely microscopic pattern. So let's forget about the continuous. Well, let's replace the continuous space with a lattice, and let's replace the U1 valued gauge field with a discrete field. So everything is discrete, everything is finite. So vector field corresponds to putting your degrees of freedom on edges in your lattice. Here, here I'm drawing the 2-dimensional square lattice, and my vector field, two-component field, is now laid down on these edges. You can introduce a scalar field. Where would you put that scalar field? Scalar, I would put it in the vertex. There's one point is also with some value, field value, so it matches. And the gauge transformation is is acting on as a gradient of some scalar value. So as the scalar value is valued on the vertices, and the gradient means that you take a difference between the two. So the gauge transformation on the pure gauge field will act on these edges in this form. If you add a scalar field in the middle, then with the regular representation of the gauge group, then I would deform, well, I will modify my gauge transformation to act on that scalar field as well. Then you seek for the gauge invariant operators in a similar fashion that people form the field strength, which is gauge invariant. We can do the same thing in the lattice. Here I form a flux operator made out of the gauge field variables, and at the same time I can introduce the analog of the electric field values and something acting on that scalar field too. So these are all gauge invariant operators. And using those gauge invariant operators, I can write down a dynamics. And here I chose a very specific, you can say it is boring because I'm going to put the zero electric field and I'm going to put mass on the scalar field. Then the corresponding Hamiltonian would read like that. There is a magnetic flux term and there's a mass term that correspond to the scalar. And you can increase the local dimension approaching that U1 valued gauge field, then you can recover the usual quantum electrodynamics in n dimension. Now, let me take a basis change because it makes my picture a little bit simpler. Starting with focusing on this specific Hamiltonian, which is kind of, you may say it is kind of boring because there's no interaction between the scalar field and the gauge field in this Hamiltonian. They're all acting on separate degrees of freedom. But still, it is useful. So yeah, so coming back to this local basis change, how do I do the basis change by C0? What is C0? C0 is a jargon from quantum computing literature, and it is acting on 2 degrees of freedom, qubits, 2 qubits, and they act in this table. Xi is mapped to xx. Here, x stands for Pauli x because my degrees of freedom are all just Z2 valued, and ix and so on. So, and the left-hand side is the generator for the two degrees of freedom. So it is now my action, my basis change is fully specified. If you do it, if you apply this C0 across these in this way, I apply it everywhere like this. So I couple the scalar field value and one edge by this C0, and you do it everywhere. You can do it. You can easily calculate that. I'm not going to do it, but you can easily show that the order of application doesn't really matter. So you can do this local basis change simultaneously everywhere. Then the gauge transformation with the matter with the scalar field becomes just a single site operator x. But fortunately, the gauge invariant operator doesn't really change, and our previous boring Hamiltonian becomes like this. And here we have the gauge transformation here, and there is something that looks redundant. So let me remove that. Then what I end up getting is the famous Toric code. So yeah, Toric code is essentially the discrete gauge theory on lattice with a massive matter field. That's the Toric. Now let's look at the ground state of the Toric code more closely. This is my terms in my Hamiltonian. I changed my basis. Previously, this C was X. I'm sorry, I should have replaced it, but I didn't. How can I understand the ground state of this? The ground state will be the eigenstate of all these operators. They were commuting operators. So after a basis change by C0, they will remain commuting, and the ground state will be simultaneous eigenstate of those. And I can start with the eigenstate where these previously gauge field operator, but since we have changed the basis, it's some mixture of the scalar and gauge field configuration. I can start with the eigenstate of individual these z's. I denoted that by emptiness here. And since it has to be the eigenstate of this flip x operators, and each of which would introduce certain loops. And being eigenstate means that you have to just take a superposition over all possible such insertion of loops, and my ground state would look like that. I could start with a different initial state in my mathematical journey to produce my ground state. I could start with a configuration where all the degrees of freedom are in the +1 eigenstate of z, except those in the horizontal line. Then introduction of a loop will not change the fact that I had a one horizontal line that is stretched over indefinitely. So that is a topological feature of my beginning state. And if I started with the vertically extended configuration of underlying field, then that fact that is a vertically extended line, that does not change. And I could do both. So there's a horizontal and vertically extended thing, and my insertion of loops will not change that fact. So topologically, there are 4 distinct sectors, and that is exactly the 4 different ground states of the Toric code.
Well, one question. Sorry. So basically, C0 operation is just a gauge transformation in G2 gauge theory language.
Yes.
So many types of some operations in quantum computation or whatever is basically in this gauge theory language can be translated into just change of a local basis function.
Changes of what?
Local basis. So for example, if I not C0 gate, if I apply to the other gate, but so I don't know now. So that also can be understood as some gauge transformation.
No, C0 is not a gauge transformation. It's a simple. It's a kind of just a frame change how I look at my field. It's completely local operation. It just changes your description, nothing about physics. And all I'm describing here will be describing just one logical qubit.
So previously showed some G2 gauge theory, and you applied C0 operation, then you obtain Toric code after removing gauge. So what does it mean? C0 is not a gauge transformation?
No.
So what is it? What does it mean? So sorry, but I just so the relation between this Toric code and the first some simple G2 gauge theory action is related by C0 operation. So can I understand? So if I so is this two Lagrangian Hamiltonian is adiabatically connected and essentially the same, or
yes?
So what does it mean? C0 operation?
It's just a basis change. I mean,
but not the gauge transformation.
It's not a gauge transformation.
Local basis change.
Yeah. It's like if you had a Lagrangian if you had a two independent fields, then you write down the same Lagrangian using, say, phi plus phi 2 and phi minus phi 2. That's a rewrite of your field. Nothing changes. And the similar thing is happening here.
I see.
So it's just a complementary view for the same thing. Literally same thing.
I
So,
see.
Can I comment something?
yes.
Yeah, I think the main reason why we actually apply CNOT is that to make some type of symmetry between X and C terms, and because the original Hamiltonian doesn't really have like a 4X terms, we want to have 4X terms and make some type of symmetry. So we want to understand the physics like a more like a clear in this case.
Yeah, it is a simplification tool. Yes.
I see. Okay, thank you.
Right. So Xiaogang Wen liked this picture so much that he put the figure of this soup of strings on his book cover. Basically this picture, how to think about the ground state wave function of a topological order is the picture is correct. It's a superposition of many various soups. You may wonder why there is many like these branching things, but that's a technical detail. You can come up with some other consistently deforming, some other consistent rule for deforming strings, and one of which may have some branching structure, which is not found in this Z2 simplistic example. Okay, let's think about the ground state wave functions in a slightly different way. Let me just fix my one ground state, starting with the vacuum. I insert loops here and there and take a superposition of all. The next one that had a topological non-trivial horizontal loop, that one is obtained from the original one by inserting this string-like operator. Now, since the presence of horizontal string is topological, my operator insertion can be anywhere as long as it matches the given topology that is horizontally extended. Similarly, I can generate this ground state from the upper one by inserting a vertical string operator, and the other one, well, just a vertical and horizontal string insertion. And that is called the logical operators. Why logical? Because it manipulates the logical state. Doesn't mean that it is not illogical. All right, so let's extend this observation that different logical states can be obtained from one another by some insertion of topological non-trivial operator.
Excuse me, I just had one question.
Yes.
So do you have some kind of a zero modes here? Like how do you, can you tell us something about it? The zero modes in your previous slides when you're defining the ground state?
Yes, zero modes. Yeah, I mean, they are all degenerate ground states. Locally, they're indistinguishable. They have exactly the same energy. So usually, when you say zero mode, that means that state with a zero energy.
Exactly, yes.
And yes, this is a state with a zero energy. Of course, the ground state is said to have energy zero.
So all of them are zero modes.
Yes. All of
But
them are.
they're topologically non-trivial.
They are topologically distinct. Therefore, these four states are orthogonal to each other.
I see. Okay, thank you.
Sure. Yeah, so the key point I want to make here is that on the Toric code, the operators that transforms one logical state to another logical state is equivalent to the one ground state. Another doesn't have to come in a definite position. It can be anywhere as long as it carries the same topology. So there are many equivalent logical operators. So there are different operators on the full Hilbert space of many degrees of freedom, but on the restricted subspace of ground states, they act exactly the same way. And more formally, for any finite region, you give me any ball, then I can find a complete set of logical operators. By complete mean that I can move between any two different logical operators by acting by some element in this complete set. And there's a complete set of logical operators that do not act on that given region. So I can always avoid any finite region. So for example, this is, say this is my torus. Then, well, if you demand that, oh, please avoid this circle region, okay, because the string operator can go around this region. If, oh, please avoid these two regions. Of course, I can do like this. I can go around like that. So any finite region can be avoided. And this feature that the logical operators can be deformed freely as long as it is fixed in topology. And for this region, or for this reason, people, well, historically different, but now I think of it like that. People call it topological order. There's a different states that you want to distinguish, but you cannot introduce any local observable to distinguish them. There are the Wilson loop operators, but that is insensitive to geometric detail, but only on topology. And surprisingly, well, not so surprisingly, the fact that you can avoid certain region is exactly what error correction requires. So here are three statements. Oh, hi, Kirill.
Hi, Jeongwan. I just wanted to ask you, isn't avoiding regions changing topology in a sense? Don't you create punctures in your plane when you decide to avoid certain regions? There might be some terminology disconnect, but to me, it seems like when you decide to avoid certain regions, that literally creates a puncture in your.
Yes, I'm very not precisely using the word around topology here. Here, the finite region is something that I want to erase. Well, maybe it's better to explain this set. Then things will be clear, I think. If not, please ask me again. So here are three statements to say that, oh, my code, my set of logical states is error correcting. When can I say that? Well, there are many modes of error introduction, but here I want to focus on the simplest. So someone like, I don't know, I'm not very good drawer. Oh, a very good drawer, but someone holds a piece of material that is supposed to hold your logical qubit. But somehow this person drops a piece of this material along the way. And now it is now erased. We call it erased. You can identify where the piece is dropped, but you have no access to what the quantum state was in this piece. But still, despite this erasure, you can recover what was the original state. You can do whatever measurement you wanted to do before this drop, by acting on somewhere else, and that I call it correctable. So that condition is equivalent to the following: there's a complete set of logical operator representatives. So remember that logical operator is some operator that induces some action on your set of logical states. And representative means that just pick something that avoids the region. Here it does not come. There's no operational meaning here. It's just the existence of certain representatives. So in this medium, this region can be avoided. Avoided meaning that there is some operator set does not act on that region. It doesn't mean that I literally introduce a hole there. It just means that in the event that I may lose that portion, right, I can access the underlying quantum state.
So I mean, if I may chime in,
yeah.
So the lines can actually terminate at that region. It just you have no way of dislodging them from there, right? So right now you're drawing the lines that go around it, but in principle, there could be a line terminating at the boundary of that region,
Right.
and you just can't move it from there. Is that the correct statement?
Oh, yeah, what you say is correct, but I don't want to make that connection to that one yet. Here,
Okay.
You're thinking about introducing boundaries on a code and puncturing hole and so on. No, it's much simpler. I'm just imagining that, suppose that qubits are damaged or something. I don't want to touch that. It's burning or something. Then my question, or as an operator of a quantum computer, you want to salvage your logical qubit. How would you do that? Can you do it? That's what criteria is referring to. And I'm saying that the ability to access the logical information is phrased in terms of existence of certain representatives that avoids that region. Yeah, thank you. Now the third condition is that the third condition is that this region, if I make an exact copy of it, hypothetically, of course, because of no cloning theorem, and if I have the exact copy of this, and if my logical state has some correlation with anything else, some other external system, then this external system has absolutely no correlation with that lost degrees of freedom. That's an equivalent condition. So I said hypothetically you could manufacture this copy, but that is also not so hypothetical. You could literally make it, because the state, the mixed state, of course, the mixed state of this little patch of a code state is independent of what logical state it was. In the Toric code example, you have no idea where if there was a horizontal line going on or a vertical line going on by looking at a small patch. The small patch have no idea about that. So that's the third condition. So having a topological order is almost synonymous in this picture clearly. Well, I want to have an error correction against the loss of certain portion. That is equivalent to being able to avoid that region, which means that my logical operator can be somehow deformed to avoid that region and so on. And this criteria, all I have said has an approximate version, so it's robust to any extra imperfections we want to introduce. And that idea has led to the famous proposal of topological quantum computation. Let me just very briefly introduce what that is. So the encoding of a logical qubit is performed to topologically degenerate excited states. You consider different ways to create the same configuration of local charges with a zero global charge. There's no notion of individual logical qubits, hence you cannot say there are 100 logical qubits, but just that there are exponentially large logical qubit space you can use. And then if you move around those excitations here and there in such a way that their trajectory is sufficiently far separated, then you are inducing certain unitary transformation on the enclosed space, and that induces some transformation in the code space. And since everything, the trajectory is playing the role of logical operator, and since it is independent of the geometric detail, the error correcting capability just kicks in. So it's automatically an error correcting code. And then at the end of the day, you measure those charges, which is locally measurable, then that outcome will be the result of computation. Compiling any generic algorithm into this proposal is a non-trivial task, but there is a known ways to do it. So that was this idea made a lot of people very excited. And now let's talk about, well, since we have understood a little bit about the 2+1 dimensional situation, we can go to higher dimensions. The discrete gauge theory developed in the early 70s that was already dealing with the high dimensions. 2 + 1 dimension is just the smallest dimension where the discussion is feasible. One-dimensional case is kind of degenerate. And that corresponds to, in a model language, higher form gauge theory. And the ground state degeneracy depends on the topology of the space. And there was an interesting model discovered in 2004 by Claudio Chamon at Boston University. This model lives on a three-dimensional simple cubic lattice. It actually uses the half of that lattice, even at sublattice of that. And Hamiltonian terms, Hamiltonian is a sum of the product of these Pauli operators. The three axes, so x separated, you put x, y separated, you put y, and separated z, you put z there. And the Hamiltonian is just some of these. You can exactly analyze the spectrum, and much more detailed analysis came almost 6 years later by Bravi, Linghuis, and Haah, and they have found that the ground state degeneracy is a number theoretic function. If you put this model on a periodic boundary condition on a three-dimensional torus, and if you had a Lx, Ly, Lz linear dimensions, then the number of ground states depends on the greatest common divisor of those. How can I have a greatest common divisor in a lattice model? That sounds weird, because we have only seen the examples where the degeneracy only depends on topology. Nonetheless, this Chamon's model exhibits topological order in the sense that it is an error-correcting code. So you could, in principle, use it as a quantum memory and all other purposes. Something even weirder exists. This is what is called the cubic model. It lives on the simple cubic lattice with the 2 qubits per site. The Hamiltonian terms are drawn like this. It is a product of 8 Pauli matrices. It is designed to be commuting Hamiltonian, and there is some non-degenerate. There is a degenerate ground space when you define the model on a torus. And the crucial feature of this model is that there is a logical operator that is somewhat flexible, that has some flavor of topology. So it is an error-correcting code, but nothing looks like a Wilson line operator. The operator that acts on the ground space must have some other geometry than line. And this model, you can think about the dual theory, but it turns out that the dual theory requires some symmetry that acts on some subsystem, not the entire global system that you would find find when you dualize the usual gauge theory. After 12 years or so, no field theory is known to describe the ground state of this lattice Hamiltonian. Probably Nari Seiberg have commented on this, that some quantum field theory should emerge as a low effective theory of a lattice model, but this gives a challenge to that dogma. Now, this model is collectively called the Fracton phases. So let's get into a little bit of properties of this code. Maybe the most surprising fact is the degeneracy formula. This cubic code model has degeneracy that is a power of 2. The 2 is coming from the fact that it is made of qubits instead of any other degrees of freedom. And here's the exact calculation as a function of the system size L, L by L lattice, L by L by L lattice, and this K behaves like this. The exact formula is known. K is given by the GCD of these polynomials in T over field of 4 elements, and some values are evaluated very well. Some values are changing very dramatically upon addition of just +1. You can talk about braiding of extended charges. The lack of Wilson line operator means that no particle is mobile. Nonetheless, you can talk about braiding. So for example, you can separate some excitation from line-like collection of charges, and you are left with the point-like. And in the process, you would have to act on some fractal-like shape. You can merge them, you can combine them in a different order, and it somehow magically disappears at the end. So if you were rotated this cube a little bit like this, then you will find a hole in that three-dimensional cube that would look like this. So, well, some extended hole like that. So there is some notion of braiding. It's just not conventional. That gives another challenge to find a field theory description of this.
Question?
Yes.
What is the operator for excitations in your lattice model? Yeah.
Yeah, operators, well, I don't have a simple explanation for those. I can tabulate them, but the table is not very insightful. There's no, I cannot explain in words. Let me put it that way.
I see. But anyway, you just apply Pauli, some combination of
yes. Since the Hamiltonian is just a product of Pauli's, the operators for this weird braiding is also.
So also, what does it mean? This fractal pattern, what does it mean?
There is some fractal-like feature, but even that is not that accurate because the operators come in various shapes, and this is one representative.
Does change of operators from the ground state here.
Sorry.
So this pattern means that just the change of values of some by excitations when they move.
Yes. Yeah.
Okay, I see. Okay, thank you. Yeah.
Another feature of this model is that you can study a kind of RG, renormalization group flow. If you started with the lattice ground state, and then you apply certain layers of unitary, the passive basis change, for the purpose of discarding some of the disentangled degrees of freedom, then you find the exact same copy at the coarse-grained level. But at the same time, you find another copy that looks like some other ground state of some other model, whichever that is. And so which is not, well, the emergence of the other piece may not be too exotic because, under RG transformation, your theory may be changing in form. But the weird thing is that there's the exact copy of itself, and still there's another copy. Such a branching structure is partly found. And this new piece can be analyzed in a similar manner, and it turns out it reproduces itself, but still becomes two copies of this. So if you were to write down, yes. There's a question?
Yeah, sorry. So is that what entanglement RG means here? Like it is something like a Mera type of, like a disentangling things? Or exactly like that. Okay.
Right. Mera circuit would look like roughly like this. So you have some input state that is coarse-grained to become the same state, but at the coarse-grained level. And this state looks exactly the same as before. So you could continue it, and it becomes expanding. It can be naturally put into a negatively curved space. But here, what you have is you have copy of itself, but there's another copy, like very schematically, like that. So you need two more extra dimension than the original space. In the usual Mera, you need only one extra dimension. Here, you need two extra dimensions.
Okay.
Which is consistent with the fact that the degeneracy is a growing function of system size.
I'm sorry, just essentially just follow-up question. So I still don't get the algebra procedure. Will you repeat again? Sorry.
I didn't explain. Right. It's a rather ad hoc calculation, but the guiding principle is that you apply certain unitary, because you don't want to project down anything. The transformation has to be unitary, and at this and you have to produce itself at a coarser lattice, and you're allowed to produce completely disentangled degrees of freedom. That's fine. So in yeah, I call it entangled RG, but in the real hands-on explanation is that there is a unitary circuit that transforms one state to another state at the IR level, but it turns out to have the same structure as before, except for the second copy in the red block.
What do you mean second copy? That part I think I didn't get.
Here. So if this was the original ground state, then I find some unitary. Somehow my pen is not working. I found some unitary in such a. I'm sorry. Okay, eraser is working. Yeah. Oh. Oh. Let me try it. Sorry about that. This thing happens. So yeah, the L is the system size, overall system size on some finite L, yeah, there is a unitary circuit that decomposes into two separate things.
I see. Thank you.
Oh, I have almost. This is an hour. I didn't expect this too long. So beyond this cubical model, people have found many different examples, and one family comes in a so-called foliated Fracton phases. The X-cube model also belongs to this class, and the idea is that these examples are obtained by coupling subdimensional states. So in particular, the X-cube model is obtained by putting the two-dimensional sheets of Toric code along all different planes here, here, and here. And you condense certain excitations at the intersections. Then the resulting model, if you condense too much, then the entire phase might be just destroyed. But if you do it carefully, then you can produce still non-trivial phase, and the result is X-cube model. And you can generalize to other layered structures of the three space. And people have constructed some non-abelian versions of this. And people have gone beyond those constructions, and the most general construction I've seen is so-called topological defect network. The idea is that you put the usual TQFT states on 3 cells, and then you condense certain combination of excitations at their intersections. The choice of this condensation should be careful, otherwise you would end up with either trivial states or completely separated 3 cells. But if you do it right, then you produce interesting Fracton state. There are 3 length scales in this construction. The microscopic lattice spacing, of course, and there's a global system size, but also there's the intermediate length scale, which controls the cell size. Now you have to ask some philosophical question. how large a cell should be. Should it be much closer to the lattice spacing, or should it be much closer to the global system size, or somewhere between? What do you mean by phase, and so on? You can spend an afternoon after those questions. So that's the brief report on the Fracton side. Actually, the whole the finding was initiated with this question: can there be a thermally stable quantum memory in 3 dimensions? And can it be can it come from some quantum phase of matter? The thermal quantum memory is drawn in a cartoon like this. So you start with some small code, and then you let it evolve under the thermal interaction. Then it suffers from some flips. So D is now become Q. And then you want to read out, and hopefully you come back to the original state. If you make a code a little bit bigger, then there is a corresponding memory time, and a similar error can be corrected. But we want that the memory time for the bigger code to be much larger than the smaller one. And we want that to be diverging function. Is that possible? This question is still open. The cubic code does not fulfill the ultimate purpose of this question. We wanted no point-like mobile particles, because if you had those, then upon the thermal contact, those thermally excited deconfined particles will become a gas. They are weakly interacting in a sense. They have topological interaction, but that's too weak to suppress any motion, so it becomes a gas, and it just destroys your logical qubit after a time that is only dependent on the temperature, not system size. And on the Fracton phase, we have removed the mobility of particles, but there are particles. So once they're excited, if you calculate the entropy factor, you just count the number of possible configurations, then still the entropy factor overwhelms the energy part. So the free energy does not have any singularity. And if you assume, and this situation is basically the best possible, topological point-like station always exists in any translation invariant Pauli operator-based code construction, and isolating a charge from the rest is only logarithmic in the separation distance. So that's the best possible. There are some recent progress on this question. Well, not precisely this question, but on the coding side. Recently, like last month, Elia Portnoy at MIT has achieved an infinite code family of parameters like this. This is a jargon from the quantum coding literature. The first parameter is the number of qubits, physical qubits in your system. Second parameter is the log of the degeneracy. So it basically is the number of logical qubits. The third parameter is the size of the operator that you have to act. The number of qubits you have to manipulate to induce any logical transformation. In the Toric code, you have to act on a line. So this parameter would be just L, when the number of qubits is L squared. And there is only 1 or 2 encoded logical qubits. But this 3-dimensional code has much better parameters. The geometry of the operators that acts on this code is hardly understood, largely because it's only 1 month old. And I think there are much work to be done. And for physicists, it's very puzzling. It's not even translation invariant. And the one instance in this family and the next instance in this family is hardly related. So what does it mean to take a thermodynamic limit? The only uniform parameter in this infinite family is the locality. There are only some small number of degrees of freedom per lattice unit ball. So then the degrees of freedom density is some fixed number. And the Hamiltonian term is acting on some small number, say 100 qubits. 100 is too large, but some fixed number. It doesn't grow with system size or anything. Those 2 parameters are only the uniform parameters in this infinite family, nothing else. Then you ask, oh, there's a question, yes.
Yeah, I'm just curious. Are thresholds of those codes well known, or like, is it possible to compute even the threshold, or like, yeah, how does it work?
So the construction is kind of indirect. So he uses two important results. First one is the existence of quantum LDPC codes. So LDPC code stands for low density parity check codes. So a code whose check operators are touching some small number of qubits, and every qubit is touched upon by some small number of checks. And this family has some constant fraction of the number of logical qubits to the number of physical qubits. And the number of qubits you have to manipulate to induce any logical operation is also linear in the number of physical qubits. So given, yeah, he's using that existence of good quantum LDPC codes. And there's another result from Friedman and Hastings that you can embed, you can write down a manifold whose homology realizes given quantum LDPC codes. There's some technical condition, but it satisfies for all known examples. And what Portnoy did was that to embed such a high dimensional manifold into low dimension with some stretching and things. So even writing down one particular example, it hardly would help. Yeah, it's a bit involved.
So basically embedded LDPC code to like a 3D dimensional system. Yes. Okay. Yeah, I see. Yeah, but we think it's topological because it has local like stabilizers.
Well, so yes, I mean it is topological in the sense that it is an error-correcting code.
Yeah, but still we don't really correct it using, for example, like matching type of decoders or something like that, right?
Oh yeah, decoding algorithm is not decoding that is not even analyzed.
Okay, I see. Thanks.
You have an opportunity. Okay. So now then, having observed such a weird or interesting or exciting phenomena in higher dimensions, we can ask back, why do we only have anyon theory in 2+1 dimensions? Why is 2 so special? Well, at this point, at this mathematical question, you can pause and should ask, what do you want to say? You could, well, you might wish to say something that, oh, if you start with some solid state and some reasonable interactions among them, then you must end up with something that is potentially anyon theory. That goal sounds very ambitious. You may start with just the lattice gap Hamiltonian, some abstract Hamiltonian, forgetting about all the solid state physics. You could do that. Or many people have just abandoned those Hamiltonians altogether and just focus on some effective field theory. And then, or some more abstract people have worked with the category theory, and some deformations among those, and try to pin down what qualifies as most physical. I'm not going to answer any of those or argue which is important, but let me just say that we have seen examples of quantum error-correcting codes that realize topological order that happens to be some anyon theory. Error-correcting codes, on the other hand, I want to say that can give some explanation. So here are a rough sketch of the status. Assume that the ground state is an error-correcting code in 2+1 dimensions. It's not really a property of Hamiltonian, but just a property of set of states, the ground subspace. Then you can show, this piece is rigorous, that you can show that there must exist point-like quartz particles. And those have to be inserted by some string-like operators. The essential reason for the string-like operator is that if you take a codimension 1 object in 2 dimensions, then you end up with a string. You can also show that there are only finite degeneracy. It should not grow with the system size. And the degeneracy must be bounded by the topology of the space. In particular, if you work with if you put your theory on a sphere that has a zero genus, then your ground state, your code space must be non-degenerate. It should not function as a logical. It does not have any logical qubits. And so this final degeneracy also is related to the assumption in the anyon theory that there are only finitely many different topological particles. So it gives some explanation why we are working with the anyon theory as we know. And the non-degeneracy of the braiding, which is a highly non-trivial assumption in the abstract nonsense theory, and that comes from the logical operator. Comes from the fact that logical operators act irreducibly on the ground state subspace. I encountered a very mathematical paper by Ogata, which I plan to read, but I do not have a confident knowledge about that, so I'm just referring to you to look at that paper. All right. So for the, well, it's supposed to be the second half, but I guess I shouldn't go too much. So let's.
Yeah, I think yeah, you don't feel any pressure. It's completely up to you.
Oh, okay. Okay. So now let's switch the gears and talk a little bit about the Floquet dynamics and related codes. Yeah, let's forget about the code for a moment. The Floquet dynamics is nothing but some periodically driven system. So there is some time periodic Hamiltonian, and we study the induced dynamics and study eigenstates of that evolution operator, quasi-energy states. And here's an interesting example of a Floquet dynamics that induces something non-trivial at the boundary. So here's a very simple, simple dynamics. It actually consists of some unitary gates. There are, qubits or degrees of freedom, not too important, but for the sake of simplicity, let's assume qubits. And then the first 1/4 of the period, there's a swap circuit going on between neighboring horizontally distant 2 qubits. And the next time, they're vertically different. The next time, now horizontal again, but now it's different. Here it was, this bond. Now that bond is gone. So it's like a 1 qubit experiences swaps from south, north, and west, and then south. Oh, did I say south? I meant east. So it goes on for that period 4 Floquet dynamics, and in the bulk, any degrees of freedom will return to its original position after those 4 swaps. But at the boundary, things are different. At the boundary, things, there's nowhere to go for the south swap, so it should stay the same. But the east and west swap will make these things move. And if you analyze the quasi-energy spectrum of this Floquet circuit, then you'll find a subsectoral mode at the edge. In the bulk, it's completely flat. Everything is stationary. So it's an identity dynamics in the bulk, but nonetheless very non-trivial at the boundary. There are variants of this idea. You can consider the type honeycomb model and drive the system in a period 3 fashion, and it basically induces the translation of chiral translation of Majorana modes along the boundary. So identity bulk in the Floquet dynamics doesn't mean it's boring. It may be very interesting at the boundary. So let's recap how this can happen in general. And for that matter, we can think about the non-empty but identity quantum circuits. By non-empty means that I have some quantum circuit. Oh, by the way, does everybody comfortable with the notion of quantum circuits? Okay, so well, it's simple. I mean, there are one layer. It consists of unitaries that acts on a very nearby qubits or some degrees of freedom, and they should be non-overlapping. And there are finitely many such layers. That's it. Non-empty means that there is some gate. There is some non-identity gate somewhere, but nonetheless, it implements identity overall. That's what I mean by identity quantum circuit. Given such a circuit, we can think about dropping of these gates on a half of the space. So I had a identity circuit. So start with the identity because I did nothing. And then I did something, but end up with identity again because I am assuming identity on the circuit. And suppose I drop those quantum gates on the half of space. Say this is now, left half, everything is dropped. But on the right, everything is kept. Now, if you think about the dynamics in the bulk, then you can draw a nominal light cone of the operator induced, acted upon by this circuit, and this gets acted by the full circuit, so it implements identity there. So this operator would not see anything. Here, well, obviously everything has identity. On the boundary, something is happening, but I don't know what that is. But I do know that it should be some local motion. I mean, there's a nominal light cone, so operator cannot go too far. It's some local dynamics. And in fact, any local dynamics, locality preserving dynamics, is realized in this way. So remember that this boundary is one dimension lower than the space where this circuit lives. Using the fact that the dynamics that is locality preserving and its inverse acting on a separate system is actually, you can realize it as a quantum circuit. It's not difficult to prove, but I'm not going to do it here. You can, using that fact, you can isolate that single alpha action by introducing one extra dimension. So locality preserving unitary dynamics is all that is at the boundary of a Floquet dynamics that is identity in the bulk. So let's go a little bit abstract then. Let's introduce that, let's just capture that notion. Alpha is going to act on my operators, act on my observables, and it should be, well, we have seen before, it comes from some unitary conjugation, so it must preserve all the addition and products of observables. So it's an algebra automorphism. And we have noted that there is an important support condition that image of an operator is supported on the small neighborhood, some neighborhood, I'll say L, some small finite meter. Yeah. Examples, of course, is the quantum circuit of some finite depth, and any short time evolution by a local Hamiltonian qualifies as a locality preserving unitary QCA. Why is it a good definition? Because those important examples that we know as a model of quantum dynamics are all of this form. Now, you can ask, is all locality preserving unitary comes from quantum circuits? The answer is surprisingly no. That has been known for some time, but here is a little bit larger class I consider. I mean, larger class of examples I consider. I was able to prove a definite theorem along this. So let me just state what that is. So assumption is I consider the infinite lattice, z to the z, d-dimensional infinite lattice, and I assume that there is some finite dimensional degrees of freedom per site that happens to be a fixed prime power, and I demand, this is an important assumption, my QCA, the locality preserving unitary, must map a Pauli operator to a tensor product of Pauli operator. This kind of map is called Clifford in the quantum error correction literature. So I call it Clifford QCA. And the result is that if you forget all the Clifford circuits and translations, because we basically, well, it's simply because I want to just forget about that because we understand them. And even after such a forgetfulness forgetting known things, there are something non-trivial, and those non-trivial form a table, a periodic table, periodic in dimension. If your underlying dimension is 2, then there is exactly one non-trivial element in dimension 3, and thereafter, every other dimension, you have exactly one instance of non-trivial thing. It doesn't happen in low enough dimensions. If you have odd prime dimensional degrees of freedom on your lattice, then there is a period 4 in dimension. And they come, and the group depends on the local dimension prime in an interesting way.
I'm sorry, I think I'm lost. What topological classification about what at this state during this Floquet evolution? I mean, what does it mean?
Well, I think I was rushing a bit. So Floquet evolution in D, say +1, that is identity in the bulk, induces boundary action that is locality preserving, which I call QCA for historical reasons. And this boundary QCA has a property that it is unitary. Second, it is locality preserving. And now you ask, if I deform this Floquet side, then what happens on this boundary action side? So that has a topological flavor. I have some object, and I'm free to deform it as long as it satisfies certain natural conditions. Then I ask what remains invariant under that deformation. Topological phases, on the other hand, it has a similar flavor. Namely, you have a gapped ground state, and you are free to perturb your Hamiltonian arbitrarily as long as the perturbation is weak. Then you ask what remains invariant under that perturbation. The typical answer has been that, oh, there is something we call anion, and there are braiding statistics, self-statistics. Those algebraic data is invariant under small perturbations on the Hamiltonian side. So that's why we call the anions are topological. Here, I'm doing the similar thing. The main object we consider is the Floquet circuit that implements identity. So, and you ask, if I deform my circuit a little bit, if I change my gates a little bit, as long as I maintain the overall identity property, then what happens at the boundary object? Is there anything remains invariant? That's the question. And it's not difficult to show that some small perturbation on the Floquet side will induce a quantum circuit on the boundary side. So you have to forget anything that is implementable by a quantum circuit strictly on that boundary dimension D. So you mod out that. And the translation, as we have seen in the first example, the swap 4 layers, that thing can be implemented non-trivially, and that is not a quantum circuit that has been known. But since we know that, I want to forget about that as well. That's my just choice. You don't have to, that's my choice. And then you ask, so okay, modulo those quantum circuits and shifts at the boundary, is there anything else? And here I claim for this restricted class of QCA, there are exactly this much, depending on dimension. Nothing else.
So then it's not a state. It's not a
right. It's not a state. It's not a state. It's a question on the discrete time evolution operator itself.
I see. Thank you.
Yes, there's another question.
Yeah, almost the same question. So how do we interpret this? For example, like it's two. There are two-fold dynamics. So there are two different dynamical modes, or like you said is not a state. Then what is it?
So that comes later.
Okay, sorry.
Yeah. That comes next slide. Okay, let me skip that part. So yeah, what does this QCA do? What does this non-trivial thing do? This is actually a disentangler of so-called Walker-Wang model. It's a crash introduction to the Walker-Wang models. You can define a Hamiltonian that happen to be exactly solvable on a closed 3 space. So you have 3 + 1 dimensional Hamiltonian. And the ground state wave function is specified by the following rule. You consider 2 + 1 dimensional annual theory, anything. It doesn't have to come from, well, it doesn't have to come from Hamiltonian, it's just an abstract thing. And there, you can calculate the transition amplitude of the various vacuum-to-vacuum processes. Then you interpret that space-time figure of anyons. So, you would draw some string diagrams for, as in transference theory, you would write down something like this. This is my space-time trajectory. Then you interpret the transition amplitude of this trajectory as a wave function amplitude in the 3 + 1 dimensional model's ground state. So here, interestingly, time is not special at all. All 3 dimensions are on a common ground. And the special emergent symmetry of the 2 + 1 dimensional annual theory implies isotropy in this 3 + 1 dimensional Hamiltonian. And here are some facts. It gives you such a ground state is stabilized by exactly solved Hamiltonian with a gap, with an energy gap, and there is a unique ground state, and that Hamiltonian is unique ground state. There's no topological excitation. All excitations are locally created. You don't need a infinitely supported insertion operator. And you can realize the input abstract annual theory as a boundary theory, also in an exactly solvable fashion. And it is believed to admit a gapped trivial boundary as well, but you have to break something in the construction. And QCA maps the ground state in the closed space to that of a trivial state. This QCA, the non-trivial QCA, maps the Hamiltonian of this Walker-Wang model to the Hamiltonian of trivial product state. That's what this QCA is doing. Okay, let's throw in more recent interests. People are interested in dynamics itself, and the unitary dynamics has been, well, that's the standard one to study. But now these days, people throw in measurements as well, because measurements are doable operation that you can do in some laboratory. Here's a figure from this review paper. Basically, you consider some spin system, unitary gates that are going on, and you insert the measurements here and there. You can tune a variety of parameters, and you can study the stat map of such systems. And depending on the measurement outcomes, you will end up with some state, and you study some universal features of those. Typically, studied subjects are the entanglement growth, be it a volume law or area law, how it evolves with respect to time, and you can study the out of time order correlators, the all-talk operators, and how they space-time distributed. And people now have interested in the how quantum information can be encoded and manipulated in this dynamics, and what can we say as a many-body physicist to such systems. That's a highly interested field. And let me remind you what local measurements can do. It can prepare highly entangled states. So the preparation of the Toric states can be done by local measurements. You don't need deep circuits, even though the ground state is highly long-range entangled. Measurements is special. And essentially all quantum error correcting codes are working this way. You wish to project towards the code space you're interested in. And recently there was some interesting experiment from Harvard experiment group, Michel Lukin's group. They managed to manipulate some ensemble of atoms and managed to prepare the ground state of a Toric code by measurements. The measurement fidelity is not that great, but it's detectable. Also, local measurement can do long-range teleportation, instantaneous teleportation. So here's a figure. So initially you had suppose you had some data qubit here, and time goes upwards, and you prepared some bare pairs across different pairs, and then you implement Bell measurements on alternating pairs. Then, depending on the measurement outcomes on those measurements, your quantum state at the site 1 will be teleported instantaneously, or quote unquote instantaneously, to the last one. You do need unitary correction based on outcomes, and this is how you avoid the special relativity's causality, because that measurement outcome should be transferred somehow. But modulo that unitary correction, the teleportation is instantaneous, and every operation is local. Now let's mix them together. And the idea resulted in what is now called Floquet codes. And here's a concrete example. Very simple. There are qubits on the vertices here, 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 like that on a honeycomb lattice. And I named. Oh, whoa. I colored the plaquettes in 3 colors, 0, 1, 2, in such a way that no plaquettes of the same color is nearby. They are connected by edge, but not by a common edge. Then what you do is you go ahead and measure for every 0 edge that connects 2 0 plaquettes, you measure, say, poly X and X. And then at the next stage, you go ahead and measure Y along 1 edges like this. The next stage, you measure CZ across the bond that connects two plaquettes. And you do it periodically. That's it. That's so the dynamics is entirely consists of measurements. And it turns out that it implements some error correcting code. So I gave you, I started this section with a discussion of Floquet dynamics. This is kind of Floquet dynamics because there's a periodic piece, but it's not unitary dynamics, it's a measurement dynamics. And I discussed some elements about QC and locality preserving unitary. What does it have to do with those? I mean, I'll come to that. But let me just remark that this Floquet codes got interest because of this fact. Usually when you design an error correcting code and implement it, there is some base code, like a Toric code or Steam code or whatever. And there is an implementation circuit that is designed to measure the syndromes and so some modes to detect errors and so on. Here in Floquet codes, in this honeycomb model, that dichotomy is gone. I did not specify any underlying code. I just specified the measurement sequence. That's it. And the careful analysis of post-processing of measurement outcomes will reveal the potential locations of error and will allow you to achieve fault tolerance. And for this simplicity, under some noise model, it performs good. In what metric good? So on the right-hand side, here's a simulation result implementing the surface code using measurements. We introduced some ancilla and we compressed the measurement circuit as much as we could, and we estimated the error threshold value that we discussed in the beginning of this talk. And on the left, this is a similar plot for the simulated for the Floquet code, the round 3 measurements. And the crossing point, the threshold value is about, here is about 1 point, I don't know, maybe 1 or 2. Here, this is like 0.2%. So about 5-fold increase in the threshold value. But I don't want to be bogus. It assumes a very specific noise model, which is applied for both simulations identically. But you should not think that the Floquet codes is the best one. It's not like that. Depending on the noise model, the usual surface code implementation may be better, but under this specific noise model, Floquet codes performs better. And why do we care about the threshold value? Despite the effort for error correction almost decades long, the current status of QEC is on the verge of break even. People claim that they have achieved break even point, but there are elements that needs to be addressed operationally, especially. And it appears that the biggest bottleneck is the lack of any scheme that has very high threshold value. And so if you could come up with a scheme that has a threshold value like 3 times higher, that'll be a breakthrough. So let's combine the previous discussion of the locality preserving unitary and the Floquet dynamics in this way. There is anomalous boundary flow in the Floquet code. So how do you detect that? Well, imagine there's a boundary, and then you restrict the circuit elements accordingly. So you drop any circuit elements that goes beyond my boundary and just keep what that is in the bulk. Then, because I have opened up the boundary elements, there could be some logical operators that appear because of the boundary. Why not? And it turns out, after some calculation, these logical operators are teleported along that measurement circuit. And you can keep track of where it goes. You have to do it. And that the motion of the logical operator turns out to be QCA. It is a locality preserving map that preserves all the multiplication, addition, dagging, and so it's a locality preserving map. And for some time, if you had a unitary one-dimensional circuit, then this locality preserving map can only have let me say again, you can define what is called index applied for this locality preserving maps. And for one-dimensional unitary circuit, the index is automatically 0. The 4 authors, the G and VW, they have shown this. And if you had a translation, as in the boundary of a Floquet circuit, then this index can take some non-zero integer values. But on this Floquet code boundary, the index turns out to be a half, which is impossible in the unitary case. So, and that's what makes, that's we find interesting, that this measurement dynamics now gives you some different, qualitatively different dynamics at the boundary, that it happens to be a unitary, although the dynamics itself is written in terms of measurements. And that explains some of the theoretical hurdle previously we had. Shortly after that, the honeycomb code was written, there was an obvious question for practicality: how could we implement the planar version? Because we're not going to have a torus in any lab soon. Well, atomic ensemble array is the different story, but usually it's difficult to have a torus geometry. So planar geometry is desirable, but we succeeded in designing such a code using measurement sequence, the dynamics, but we had to double the period. We had some understanding, we had some heuristic, we had some argument why it has to be case, but this index theory gives you a definite answer. If you have a boundary and you want to make an error correcting code, then the index must vanish. Otherwise, there is a flow of quantum information along the boundary that is not protected, or your your measurement circuit will be implementing some very non-local operation, like a teleportation. The problem of the teleportation, the iterated instantaneous long-distance teleportation, is that in order to actually read the final outcome, you need the measurement outcomes along the way altogether. If you get one bit wrong, then your final state is wrong. So it's very prone to any errors. So you don't want such a non-local map at the boundary. And to avoid that, you have to double the period. That's the conclusion from studying the index. Okay, so some concluding remarks. The absence of a local order parameter, which has been used as a definition of topological order, is actually now synonymous to an error correcting code. Some gauge theories, discrete gauge theories, especially with the addition of matter field, can be regarded as a quantum error correcting code, and that is the Toric code. And the converse influence has been observed that quantum error correcting codes has given new type of phases, quantum phases. We're still struggling to organize them. We're still struggling to find the continuous field theory description of those. Maybe there isn't, but then what do we have to do on the bridge between lattice theory and continuous field theory side? In the perspective from the quantum error correcting code gives some explanation why 2+1 is special. The topological quantum field theory, or the abstract algebraic annual theory, as we know, emerges for a low-dimensional extreme case. A full story is yet to come. I don't claim I have fully proved that the TQFT must emerge in any gapped 2+1 dimensional theories. And there is a sociological element that where we should take the starting point of a theory is, but modulo those, quantum error correcting code perspective gives some explanation, and I'm happy with that. And then in the second part, we discuss some of the Floquet dynamics, and there's interesting action, even at the boundary that has a topological nature, even though the bulk action is identity. The techniques, although, well, I didn't explain, but techniques from the quantum error correcting codes enable some classification in the unitary, especially the Clifford QCA unitary case. We have a full table depending on the dimension. And the measurement changed the story a little bit. There is a different kind of boundary action that is not possible in the unitary case. All this is very intimately related to quantum error correction, and we should seek, this cross-fertilization should go on. I expect much richer story in higher dimensions, and yeah, thanks for your attention.
Thank you very much, Jeongwan. So very enthusiastic and detailed explanation. Thank you. So any questions, please? Yes, Topom.
Yeah, so thank you very much for your talks. So I have a question about the cubic code and related models in 3 dimension.
Yes.
So you mentioned that the topological degeneracy there cannot be explained from like Wilson loop picture.
Mm-hmm.
But I mean, when people try to explain like topological degeneracy in Toric code or other 2-dimensional topological phase, I mean, they usually use these kind of things like anionic statistics, bulk diagnostics for, from which you can derive the topological degeneracy.
Mm-hmm.
So I'm just wondering, like, does this kind of analogous bulk diagnostic exist for these kind of 3-dimensional model, or I mean, the fact that you don't have Wilson loop kind of picture for the topological degeneracy actually suggests that this kind of thing does not exist?
So the appearance of this weird behavior happens all the way starting from 3 dimension. Any dimension you can cook up a very similar story. There is so I have shown you like this figure that something analogous to the two-dimensional braiding exists in this weird model. But you may have noticed that the operator that enables this braiding has a very special shape. It does not have a full-fledged topological feature. It has some flexibility. As long as those red regions are anchored, the middle bluish operator content can change a little bit, but not as flexible as you would wish for topological membranes or strings. And that rigidity is the origin of the complicated degeneracy formula. Well, another way to think about that, the complicated formula, is that the topological particle in this model would want to wrap around your system to come back, but because it has to bifurcate or triplet and somehow combine them all together to come to an original position. Depending on the boundary condition, that may not be possible. It's not as flexible as in the topological sector again. So for some boundary condition, the return is possible, but one side longer, you would want to return, but it somehow spread it out. I'm not sure if I have satisfactorily answered your question, but yeah, the braiding picture is really, really special if you impose a lot of constraints.
Okay, thank you very much.
More questions? I think I still don't get the meaning of index in the Floquet particle. Yeah.
Meaning of what?
Index, I mean, so classifications. Sorry, even in not in the level of measurement, even in the unitary case. Yeah. So what does it mean? Sorry. Yeah.
Well, so let me make an analogy with the
So is it related with some observable? Or yeah.
No, it's no. Okay, so yeah, it's really different. It's not a state. It's not about state. It's really about unitary itself. So you consider. Excuse me. Well, let me try to put it this way. We model unitary as a Hamiltonian evolution. I'm sorry, we model the time evolution by, time evolution is assumed in quantum mechanics, generated by Hamiltonian. Right? That's part of the assumption of quantum mechanics and all physical theories. But if you focus on just a special relativity, then maybe you only need the locality preserving property, that things that are separated cannot interfere after a short time. So if you only assume that, then possible dynamics, well, let's forget about the continuity for a moment. So possible discrete dynamics can be captured by the assumptions that, it should map the operator algebra into some other operator algebra, which has to be the same as before, and it has to preserve locality. Now you ask, well, given such a generalized consideration, you ask again, does my time evolution discrete time evolution come from Hamiltonian? And the answer is no. The translation is an example. Translation is not generated by any Hamiltonian. Then, well, okay, I understand what translation is. Then you ask, is that all? If I assume discrete dynamics, if I assume just a locality preserving property, and I mod out by anything generated by local Hamiltonian, then what remains? What other things can I achieve? And this table tells you that, if you forget about, well, in this restricted setting, if you forget those analogous to the Hamiltonian evolution, then there are exactly only some small number of those, depending on dimension.
So roughly, so it may tell us that some allowed some operators and some classified some types of theories allowed by this Floquet type evolution.
Well, well, the word theory is kind of world theory in some subject is equivalent to a Lagrangian or Hamiltonian, but in this case, no, I don't consider any such dynamical. I don't consider any dynamical generator specifically. I consider all possible locality preserving discrete dynamics. I emphasize discrete. And you want to know, you want to tabulate them, modulo what you already know.
Anyway, yeah, let me consider. Thank you very much. Yeah. So, 5 more questions. So already very long time. I think this is very good chance for us. So if you have, so maybe final chance. Yeah, I think almost we are in the lunch time. Yeah. Anyway, yeah. Then if you do not have further questions, let's end today's colloquium. Thank you very much, Jeongwan. Yeah, I really appreciate your, enthusiastic, colloquium. Thank you.
긴 시간 감사합니다.
Yeah, let's end today. Thank you very much. Yeah.
See you.